Hello everyone, I will talk about internetwork communication in this lesson. This first section will help you understand how networks are connected to each other and how to communicate between networks using Cisco routers and switches. When we connect two or more LANs or WANs through a router and create a logical network addressing plan with a protocol such as IP, we create a network community. Now let's look at the basics of internetwork communication. Networking has grown rapidly over the past 30 to 35 years, starting with basic user needs such as data and printer sharing, but now there have been rapid developments in our networks to meet needs such as video conferencing, video sharing and movie viewing platforms. Considering that nowadays the people who need to share network resources are no longer in the same office environment, what needs to be done is to connect multiple networks so that all users can use these network resources. In large networks, we may have to divide them into smaller networks to reduce user response time according to the need, because the network will get heavier as it grows. With all this growth, the congestion in the LAN will be very high. The solution to this is to divide the really big networks called network segmentation into smaller networks, and we can do this by using devices such as routers and switches. The figure here shows an example of a simple network connection for home users. Let's take a look at the main causes of congestion in our network. Congestion can occur in our network due to reasons such as having a large number of users in a broadcast domain, broadcast storm, multicasting, low bandwidth, adding a hub to connect to the network, a heavy ARP traffic. Today, routers are used to route data packets from one network to another to connect networks together. There are two advantages to using routers on our network. The first is that they do not route broadcasts by default, and the second is that they can also filter packets with layer 3 information, such as IP address. The routers we use in our network have four main functions. The first function is to make packet switching, the second function is to filter the packet, the third function is to ensure internetwork communication, and the fourth function is to make the path selection. Layer 2 switches switch packets using frame packets, while routers, unlike layer 2 switches, switch packets using logical addressing in layer 3. Routers can also provide packet filtering using access lists. Routers use logical addressing IP version 4 or IP version 6 to connect two or more networks. This entity is called a collection of networks, and finally, routers use a routing table to choose routes and route packets to remote networks. Unlike routers, switches are not used to create a network community, but to add functionality to a network. The main task of a switch is to make the local area network work better by providing LAN users with higher bandwidth and increasing their performance. Switches do not route packets to other networks as routers do, instead they transmit packets by switching from one port to another. The figure here shows an example of a simple corporate network connection. Here we have a corporate network, here we have access point and wireless clients. We provide access to these clients through access point. In this tutorial, we talked about what router and switch do in a network. Layer 2, Layer 3, multicast, ARP and broadcast are among the topics we mentioned here. You will learn all of these terms one by one when the topics come up. What we are going to focus on here is what are the main functions of the router and switch, which I tried to explain in this lesson. Goodbye to see you in our next lesson. Hello everyone, in this lesson I will talk about the TCP/IP networking model. The Transmission Control Protocol and the Internet Protocol family were developed by the Department of Defense both to ensure data integrity and to protect and maintain communications in the event of a war, so a TCP/IP network can be truly reliable and flexible if designed and implemented correctly. Now let's look at the history leading up to TCP/IP. Networks today use the TCP/IP networking model, but previously there were not many network protocols, including TCP/IP. Manufacturers created their own network protocols, and these protocols worked only on computers they manufactured. For example, in the 1970s and 1980s, the computer company with the largest market share in the market was IBM. IBM released its System Network Architecture network model in 1974. Other vendors created their own private network models, and if you bought computers from all three companies, you could communicate by creating three different networks and then connecting those networks together. In the late 1970s, the Open System Interconnection, or OSI reference model, was created by the International Organization for Standardization, or ISO, to remove this limitation. The OSI model was developed for the interoperability of networks of different manufacturers. The OSI model is a primary architectural model for networks. OSI describes how to transfer data and network information from one application on one computer to an application on another computer through the network environment. Here's how each manufacturer used its own network protocol in the 1980s. IBM computers would create a network between themselves, other manufacturers would create a network between themselves, and then you could use it by networking between all three manufacturers. By the 1990s, TCP/IP was slowly becoming more and more widespread. Devices using IBM were again creating a network among themselves, and other manufacturers were creating a network among themselves, and then we connected these networks using TCP/IP. By the 2000s, all manufacturers started to use TCP/IP and our devices started to communicate over TCP/IP. On this page, let's give an overview of the TCP/IP networking model. The TCP/IP model is a broad protocol model that allows computers to communicate, and RFC documents are used to define these protocols. Another institution is the IEEE, which specifies the IEEE Ethernet standards, and the RFC determines the protocols. Let's look at the TCP/IP and DoD model. The DoD model is basically a condensed version of the OSI model, consisting of 4 layers instead of 7. Process application layer, host-to-host layer, internet layer, network access layer. Here he shows the comparison of the DoD model and the OSI model. In the DoD model, the first layer is the network access layer, the second layer is the internet, the third layer is host-to-host, and the fourth layer is the process application layer. Here the first layer of DoD corresponds to the first and second layer of OSI, where the second layer of the DoD model corresponds to the third layer of the OSI model, where the third layer of the DoD model corresponds to the fourth layer of the OSI. Many protocol series come together in the process application layer of the DoD model to define the various activities and tasks described by the top 3 layers of OSI. The process application layer defines node-to-node application communication and controls user interface arrangements. The host-to-host layer is parallel to the transport layer of OSI, dealing with issues such as creating secure end-to-end communication and error-free transmission of data. The internet layer corresponds to the network layer of OSI, defines protocols related to the logical transmission of packets throughout the entire network, deals with the IP addressing of user machines, and functions such as routing packets across multiple networks are performed at this layer. The network access layer, on the other hand, monitors the information circulating between the user's machine and the network, corresponding to the data link layer and physical layer in the OSI model. The network access layer controls hardware addressing and defines protocols for the physical transmission of data. On this page, let's talk about the application layer in TCP/IP, layer 5, where users actually communicate with the computer. This layer is activated only when there needs to be access to the network in a short period of time. TCP/IP, it's like a network interface card. You can remove all of the network card components from the system, but you can still use a web browser to browse local HTML pages. But if you try to do things like browse an HTML page that needs to be searched using HTTP or download a file via FTP or TFTP, the web browser will try to access the application layer and respond to such requests. The application layer is also responsible for identifying appropriate communication partners and determining whether sufficient resources are available, tasks that are important because sometimes applications require more than just desktop resources. Examples include file transfers and email, which will require remote access, network management activities, and client-server operations. When we look at the figure here, we can see how the HTTP protocol mechanism works. Here user Bob opens the web server and sends the web page request to the web server here. On this server Bob returns this page to the user. So how do these processes take place? The web browser here HTTP header also transmits the address of the page at once here with the HTTP GET request message. The server here says OK to the HTTP header and transmits the desired page to the Bob user here. After transmitting the page he wants, Bob transmits the data in this page to the user here, and simply the working mechanism of the HTTP protocol works in this way. Let's talk about TCP/IP transport layer on this page. The services in the transport layer divide the data from the application layer, reassemble it and combine it into the same data stream, provide end-to-end data transfer services, and establish a logical connection between the sender and the destination in a network community. The TCP and UDP protocols operate at the transport layer, while TCP's reliable UDP is an unreliable service, so application developers need to choose between 2 protocols when working with TC/IP, either they will use TCP or they will use UDP. The transport tier is responsible for providing mechanisms for multiplexing top-tier applications, creating sessions, and shutting down virtual circuits. It also provides transparent data traffic and hides the details of the information about the network from the top layer. You can see examples of TCP and UDP port in the figure here. The port number of the FTP application is 21 and it uses the TCP protocol. The TFTP application uses port 69 and the UDP protocol. DNS, on the other hand, uses port 53 and can use both TCP and UDP. This is our transport layer, and this is our application layer. All of the applications we use here have a port number, and these port numbers use either TCP or UDP. On this page, let's give you an example to better understand TCP and UDP, and we can give you an example of a phone call to help you understand how TCP works. We know that before we start talking to someone on the phone, we first need to establish a connection with the other person, which is similar to a virtual circuit set up with the TCP protocol. If you give someone important information during your call, you can say, "Do you know?" or "Do you understand it or not?" Saying such things is similar to many TCP confirmation packets designed to verify you. Sometimes people also ask if you are still there, and at the end of the interviews, they finish the call saying goodbye. TCP/IP performs exactly the same functions. Using UDP is similar to sending a postcard. To do this, we do not need to establish a connection with the other party first, simply write our message, specify the address to which the postcard will go, and we mail it. This is similar to the connectionless orientation of UDP. We do not need a confirmation from the sender of the message on the postcard, as it is not a matter of life or death, so it does not require UDP confirmation packets. In the figure here, the user in the web browser first sends TCP/SAN packets to the web server returns TCP/SAN packets to him, and then in the third stage, the web user sends the confirmation message, that is, ACK packets, and performs the TCP connection with the three-way handshake, that is, the three-way handshake. On this page, let's talk about TCP/IP network layer, layer 3, also known as network layer. Layer 3 manages device addressing, tracks the location of devices in between, and determines the best way to move data. That is, the network layer is responsible for transferring traffic between devices that are not locally connected to each other. Routers are layer 3 devices and operate at the network layer and manage routing services in a network community. First, when it receives a packet from the router interface, it checks the destination IP address and checks to see if there is a route for that address in the routing table, and if there is a route in the routing table for that address, it frames that packet and sends it to the egress interface. If there is no record in the routing table for the destination address to which the packet will go, the router cancels the packet. Two packet types are used at the network layer. The first is data packets and the second is route update packets. Data packets are packets used to transfer user data across a network community. The protocols used to support data traffic are specified as routed protocols. Examples of routed protocols are IP version 4 and IP version 6. Route update packets are used to update network information on neighboring routers connected to all routers in the network community. Protocols that send route update packets are referred to as routing protocols, with commonly used routing protocols being RIP, RIPv2, EIGRP, and OSPF. Route update packets are used to help create and maintain routing tables on each router. The figure here shows a simple example of IP routing, where the LARI user's IP address is 1111 and the destination address is 2222, so Bob will send a packet. Here, this user sends the IP header to the router checks the destination IP address here. If there is one in the route table, it sends the packet to the router 2 from that output interface, and the router 2 forwards the packet to the user, and in this way, a simple routing process is provided. On this page, let's look at the data link layer and its physical layer with TCP/IP. The data link layer provides the physical transfer of data, but also handles functions such as error reporting, network topology, and flow control. The data link layer uses the network hardware address and is responsible for converting messages from the network layer into bits for the physical layer. At the data link layer, users use their MAC addresses at the data link layer to send packets to other devices on the local network and transfer packets between these routers. Finally, when we come to the lowest layer, the physical layer has two tasks, sending and receiving bits. The bits come and go only in a numerical Morse code at the value of 1 and 0. When we look at the figure here, in the first step, Larry creates the Ethernet frame by encapsulating the IP packet between an Ethernet header and the trailer. In the second step, Larry physically transmits these Ethernet frame bits using the electricity flowing through the Ethernet cables, and in the third step, the router physically receives an electrical signal through a cable and tries to reconstruct the same bits by interpreting the meanings of the electrical signals. In the fourth step, router 1 separates the IP packet from the Ethernet frame by discarding the Ethernet header and tray, so that the data is transmitted at the data link layer and the physical layer. Let's talk about data encapsulation on this page. As you can understand in what we have explained about how all layers perform their functions, we can express it as a data encapsulation process to the process of adding its own header information to the data provided by each top layer when sending data. In TCP/IP, sending data to hosts is a 5-step process. The first 4 steps are related to the encapsulation performed by the TCP/IP layer. The last step is the physical transmission of the data by the host. As you see here in the first step, the application data is created and encapsulated with the required application layer titles. For example, the HTTP OK message can be returned in an HTTP header and then in part of the content of a web page, while in the second step, the data provided by the application layer is encapsulated in a transport header, usually using a TCP or UDP header for end-user applications. When we go to the third step, the IP header is added to the information coming from the transport layer in the network layer, and after the IP header is added, the Ethernet header is added to the beginning of the packets from layer 3, 4, and layer 5, and the data link layer and the trailer is added to the end, and finally the first layer, i.e. the physical layer, is transmitted to the opposite device with electrical signals. We call this data encapsulation. That's all we have to say in this lesson, so goodbye to see you in our next lesson. Hello everyone, in this lesson I will talk about the OSI reference model. One of the best functions of OSI regulations is that it helps transfer data between completely different user machines. For example, a Unix host allows us to transfer data between a PC or a Mac, although OSI is not a physical model, but rather a set of rules that application developers can use to build and complete applications running on a network. Network setup standards also form a framework for creating and defining communication plans between devices and networks. OSI consists of 7 layers divided into 2 groups. The top 3 layers describe how applications on edge devices communicate with each other and users, and the bottom 4 layers describe how to transfer data end-to-end. The application layer is responsible for the communication of applications between the computer and the user interfaces, as well as the user machines of the upper layers. None of the upper layers know anything about the network setup and network addresses, which is the same with TCP/IP, which is the responsibility of the bottom 4 layers. When we look at the figure here, we can see that there are 4 layers working that explain how data is transferred with the help of switches and routers and over a physical cable. These sublayers also specify how a data flow from the source host is generated again in the destination host's application. Secure or unsafe distribution is ensured at the transport layer, and the error correction process is run before being transferred again. In the third layer, the logical addressing used by the routers and route determination is provided, and in the data link layer, the packets are combined into bytes and from bytes to frames to access the media tool using MAC address. Error detection is provided, but error correction is not provided. On the physical layer, bits are moved between the devices, where voltage, cable speed, and cable pins are indicated. Here it shows the comparison of OSI to TCP/IP. We have 5 layers in TCP/IP. We have 7 layers in OSI. The top 5th, 6th, and 7th layer of OSID corresponds to the 5th layer of TCP/IP. The 4th layer of OSID corresponds to the 4th layer of TCP/IP. The 3rd layer to the 3rd layer. The 2nd layer to the 2nd layer, and the 1st layer to the 1st layer. Looking at the figures on this page, you can see an example of what works in each layer in the OSI reference model. Let's look at the 3rd layer as an example. In the 3rd layer, protocols such as IP, ARP, IPsec, SEMP, IGMP, OSPF are working. In the 4th layer, protocols such as TCP, UDP, SSL, TLS work, while in the application layer, applications such as DNS, HTTP, point-to-point, email, SMTP, Telnet work. When we look at the shape here, it is a shape that shows how data comes out of a user's computer and accesses the other user. This figure explains the OSI reference model very well, friends. Here, the data exits the user, adds its own information in the application layer, and the information of the presentation layer is added in the lower layer, goes from the presentation layer to the session layer, and the session layer adds its own information to the application and presentation layer and sends it to the 4th layer below. Each layer adds its own information, and when it comes to the 2nd layer last, the 2nd layer adds Ethernet header and trailer information and sends it to the other side via electrical signals. The network interface card of the device on the opposite side first throws the Ethernet header and trailer information and transmits it to the network layer by combining these incoming 1 and 0 bits, the network layer to the transport layer to the session, presentation, application, and the data we send is reflected from the user's monitor to the screen. The OSI reference model is also like this briefly. Goodbye to see you in our next lesson. Hello everyone, before looking at Ethernet standards in this lesson, let's look at a typical SOHO network and a typical corporate network. SOHO, small office means home office. When we look at the shape here, imagine that we have 10 to 15 users in a home office or a small office. We need to physically connect these 10 to 15 users to each other with a switch first, then connect these users to each other and then connect them to our switch through a switch and connect them to our switch and simply connect the users to the internet by connecting them to our switch. We can take it out. Here we use copper cables. We can have a 1 gigabyte or 100 megabit Ethernet connection. Now let's look at the enterprise. As you can see in the figure here, the corporate is a little different. Here we have first, second and third floors. First of all, a router to connect to the internet, then the distribution switch. The switch on each floor connects to the distributor switch. The cable from the third floor comes to the distribution switch. The cable from the second floor comes to the distribution switch again. The first floor comes here like this. Then we connect access points on each switch so that our wireless devices can be connected, and on each floor we adjust the access points according to where the signal can reach everywhere. Typically, this is how the corporate network is formed. We bring users to the switches on each floor with copper cables in this way. If we want the cables from the third floor to the second floor, we use copper if the distance is saved. If our distance is long, we use fiber cable. In our next lesson we will look at these Ethernet cable types. Now let's go to our next page and look at the Ethernet standards there. Ethernet was first developed by a group known as DIX, which consists of the companies Digital, Intel, and Xerox, and they form a group called DIX, which led to the emergence of the first Ethernet. This first Ethernet was at a speed of 10 megabits, and when we look here, you can see the types of Ethernet. When we say Ethernet, you can understand that it is 10 megabits per second. When we say fast Ethernet, 100 megabits per second. When we say gigabit Ethernet, 1000 megabits per second, that is, 1 gigabyte. In the same way, there is a fiber and a copper one. When you use it as copper, you can use it up to 100 meters depending on the type of cable. We will talk about these in the Ethernet cabling lesson. There is 10 gigabytes, which again goes up to 100 meters, or it also says the standard numbers that the IEEE has given. When we look at the figure here, you can see an example of sending data using different Ethernet standards and different cable types. When our first user here transfers data to the third user, he uses UTP cable and 10 megabits per second Ethernet, and the switch here supports 10 megabits per second Ethernet and works 10 megabits per second between them. The user sends the data at a speed of 10 megabits per second by adding an Ethernet header and trailer to the beginning, and the switch transmits this packet to the second switch over the 1 gigabit per second fiber connection used between the two switches. A 10 gigabits fiber connection is used between switch 2 and switch 3. Fast Ethernet was used between the 3 switches and the user. As you can see, the standard of Ethernet changes here, but the operation it does not change. In the same way, Ethernet adds the header and trailer information and sends the data, so the data is simply sent. On this page, let's look at the most used types of Ethernet today. 1000 base T, defined by the IEEE 802.3 AB code, Cat5 and Cat6 cable can be used with 4 pairs of UTP cables up to 100 meters. The 1000 base SX transmits our data using a laser with a multi-mode fiber cable using 62.5 micron or 50 micron core. Our data is transmitted by electrical signals in copper cables and by LED or laser light in fiber cables. This is single-mode fiber. These are the most commonly used. 10 gigabytes connections are becoming common, but now 1 gigabyte connections are widely used. For now, this is our next topic, Ethernet cabling. See you guys in Ethernet cabling. Hello everyone, the subject of our lesson is Ethernet cabling. There are 3 types of Ethernet cables. The first type is straight cable, the second type is crossover, and the third type is rollover cable. We use rollover cables in Cisco's console cables, and we use straight cables when connecting a host to a switch or hub, and we use straight cables when connecting a router to a hub. Now let's look at crossover. We use this cable when we connect devices of the same kind to each other. For example, when we connect a switch to a switch, we use a crossover cable. When we connect a hub to a hub, we use a crossover cable. There are no more hubs today, but you come across a crossover cable that you connect them. When you connect 2 hosts directly to each other with Ethernet cards, you also need to use a crossover cable. When connecting a hub to a switch, we said you need to use a cross cable again. When connecting a switch to a switch, we said you need to use a cross cable. But this is now an old one. Now there is a feature we call AutoMDix in the new switches. This feature we call AutoMDix turns the cross cable into straight cable. We already use straight cable from switches to direct hosts. We use straight cable from switches to switches anymore. We do not use cross, but when you connect a router to a router, you should use a crossover cable. Now here it shows the connection pins of the 10 megabytes and 100 megabytes straight cable. Here pins 1, 2, 3 and 6 are used. In the same way here 1 corresponds to 1, here 2 corresponds to 2 here. This is how we connect our straight cable. Here is also the example of the crossover cable. In the crossover cable 1 to 2 goes to 3 to 6, and the 3 to 6 comes to 1 to 2 like this. In this way it is connected diagonally between the two switches, but as I said, there is now an auto-mix feature. Because of this feature, you don't need to use the cross cable anymore, you just need to use straight cable. Let's look at the types of copper cables on this page. Copper cabling is a very important part of our network, because the big reasons for the performance losses in our network are due to the bad wiring of this cabling. There are standard Cat5e, Cat6, Cat6a, Cat7 and Cat8s for structured cabling systems. Cat6as, 7s and 8s are mostly used by the data center, but we generally use Cat6 cable for our regular users. Cat6 cable works for 1 GB connections. There are twisted cables that we call screened, there are foil bending cables that we call unscreened, there are cables that have double screens, these are UTP and SFTP. Here too, there are standards as a category, what we call Cat5 cable, what we call Cat6, Cat7 cable and Cat7a cable. With Cat5e we can do 1 GB of Ethernet connectivity, with Cat6 we can do 1 GB of connectivity, with Cat6a we can do 10 GB of Ethernet connections. In the same way we can do 10 GB of Ethernet with Cat7a, we can do 10 GB with Cat7a. Now here we have examples of cables, let's take a look at them. Here we have Cat5 cable, Cat5EU/UTP. UTP means multi-pair cable with bent without screen, that is, as you can see, there is nothing inside the cable, there are only cable wires. We have 4 wires, blue is white, orange is white, green is white, brown is made up of white, and this cable is 0.5 mm. Now let's get to the Cat6 cable. As you can see with the Cat6 cable, here, unlike the piers, a plastic is put between the piers and separated by plastic, which is the Cat6 UTP cable. Here we also have Cat6F/UTP cable, which is a twisted multi-pair cable with F/UTP display and an external foil display. There's also Cat6U/FTP, which is shielded on the cable and all the piers are wrapped in foil. Here too we have Cat6F/FTP, which are the most commonly used cables, all piers are wrapped in complete aluminum foil. There is also Cat6S/FTP, this cable is also armored. If you have mice in your building, you can use this cable against gnawing. But these cables are not preferred much because they are a little expensive. The most preferred cable today is Cat6U/UTP. Here you can also see the codes of the cables, where the first X indicates the external protection, the next X indicates the protection of the pairs, the next X is the symmetrical pair. Our cables are like this in a nutshell. In our figure here, RJ45 shows connector pinouts, which have 2 types of standards. The first is 568A, the second is 568B. Usually the 568B standard is used, 568A is not used much. This is how the cable arrangement is made. The first port is orange and white, the second port is orange, the third is green and white, the fourth is blue, the fifth is blue and white, the sixth is green, the seventh is coffee white, and the eighth is coffee. You can also do the cross connection as you see here. One side of the cable starts with orange and white orange, the other side starts with green and white and green. In fact, the greens and oranges are moving, you make one side the same as the straight cable, and on the other side you replace the oranges and greens, then the crossover cable is the cable. Let's look at fiber optic cable models on this page. Let's first look at multi-mode fiber. Multi-mode cable has OM1, OM2, OM3, OM4 types. New names were given as new models came out. We can go up to 550 meters with multi-mode fiber. We can use 10 GB speed if we want. We can also use 100 megabytes, and in 100 megabytes it can go up to 2 kilometers. Here you can also see an example of a multi-mode cable, which is 62.5 microns. This means that 50 microns are used in OM2, OM3, and OM4, while 62.5 microns are used in OM1. Now let's look at OM1 multimode fiber first. OM1 multimode has a core size of 62.5 microns, can support 10 GB Ethernet up to 33 meters long, but is mostly used for 100 megabit Ethernet applications. OM1 usually uses LED light source. Here you can also see the years when the models came out: OM1 in 1989, OM2 in 1998, OM3 after 2002. You can use 10 gigabits connections in OM3, 1 GB in OM2, 100 megabit in OM1. After 2009, the OM4 came out, with which we can use 40 GB and 100 GB connections. It says 2014 for OM5, but I haven't seen many OM5s in the market. Maybe it can be used exclusively in data centers, but OM3 is generally used in the market now. OM3, 10 GB works for us. OM2 multi-mode fiber also uses LED light source and 50 micron cores, supports 10 GB Ethernet up to 82 meters long, but is more commonly used for 1 GB Ethernet applications. The OM3 multi-mode fiber comes with a waterproof jacket. Like the OM2, the core size is 50 microns, but the cable is optimized with laser-based equipment. OM2 uses LED light, but OM3 uses laser-based equipment. OM3 support 10 GB Ethernet up to 300 meters, and OM3 can support 40 GB and 100 GB Ethernet up to 100 meters, but are widely used in 10 GB Ethernet applications. OM4 fiber is fully backwards compatible with OM3 fiber and uses the same outer sheath color. OM4 VSEL has been specially developed for laser transmission. OM3 supports 10 GB Ethernet up to 300 meters, while OM4 can go up to 550 meters. OM4 can run 40 and 100 GB Ethernet up to 150 meters with MPO connector. MPO connectors are connectors where fibers are used collectively. Let's look at the OM5. This model, known as broadband multi-mode fiber cable, is the latest multi-mode type. OM5 is also backwards compatible with OM4. It uses 50 micron core size like OM2, OM3, OM4. It is designed and built to support up to 4 VDM channels at a maximum speed of 28 GB per channel from the 850 to 953 nanometer window. Let's look at single-mode fiber on this page. There are also two types of single-mode fiber. The first is categorized as OS1 and the second is OS2. OS1 and OS2 are single-mode fiber optic cables used in wavelengths of 1300 microns or 1550 nanomicrons with a maximum depreciation of 1 dB per kilometer and 0.4 dB per kilometer respectively. In this figure, 8 to 10 micron single-mode fiber appears. Usually 9 micron fibers are used in the market. Here you can see the kernel comparison of single-mode and multi-mode. As you can see here, single-mode has 9 micron cores, here also multi-mode OM2. OM3 OM4 has 50 micron cores, here the core of OM1 is 62.5 microns. As for the advantages of single mode provides longer distance transmission, has advantages such as larger bandwidth capacity, increased transmission speed, limited data distribution and external interference. And with fewer signal attenuations, single mode's OS1 fiber is designed for use with indoor applications on campuses or data centers because its maximum distance is 10 kilometers. But because OS2s are up to 200 kilometers away, telecom companies use more OS2 types for underground cabling. OS2 fibers also support 40 GB and 100 GB Ethernet. In this lesson, we talked about multi-mode, single-mode, and copper cables. We usually connect the end users to the switches by pulling copper cables from the switches to the end user devices, and we use multi-mode cables to connect the switches together in the building. If the distance between the switches exceeds 550 meters, then we can use the single-mode cable. You can use up to 10 kilometers if you use OS1 single-mode, and up to 200 kilometers if you use OS2. OS2 cables are usually used by telecom companies in places such as campuses, universities, hospitals. If the distance exceeds 550 meters, you can use single-mode cable. Goodbye to see you in our next lesson. Hello everyone, in this lesson I will tell you about Ethernet frames and sending data. Ethernet frames are used in the data link layer to encapsulate packets from the network layer, and the data link layer is responsible for converting bits into bytes and bytes into frames. Now let's examine the Ethernet format here. Where you see it in white is the data from the network layer. It takes the data from the network layer and puts it into a frame, an Ethernet frame, and adds a trailer at the end of the header to the head. That is, it creates the Ethernet frame format by encapsulating the data packet intervening. In the trailer part at the end of the package there is a frame check sequence number, which we call FCS, which gives the packet a sequence number. This number is a control mechanism used to check whether there is a change in the packages or not. In the header, the destination MAC address, its source MAC address, preamble and SFD information are added and the Ethernet frame is created and transmitted to its destination. One of the terms we will use the most throughout the training is the term Ethernet frame. That is, the Ethernet frame encapsulates the packet from the network layer and transmits electrical signals through the physical layer to the opposite device. Now let's look at Ethernet addressing. In the data link layer, the switches communicate through their MAC addresses, that is, they communicate using the destination and source MAC addresses. Let's look at this on our next page. The Ethernet address is the hardware address of the network interface cards, which we call the MAC address. These MAC addresses consist of 48 bits or 6 bytes. These MAC addresses are given specifically for each hardware, like social security numbers. It is a unique address. Now let's look at the MAC address example here. The MAC address consists of 12 values in total and is 48 bits. The way it is written is the same as here. MAC addresses are used up to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E and F. The letter A corresponds to 10, 11, 12, 13, 14, 15. That is, it corresponds to A10, B11, C12 as decimal value. The first 24 bits of our MAC address are given specifically to the brand itself. The first 24 bits of each brand's MAC address are fixed, that is, the MAC address of each brand is unique. In the second 24-bit part, the company determines itself. Let's look at how to transmit a packet using a full duplex connection. First, we encapsulate this data by taking it into the Ethernet frame, where the Ethernet header also has the MAC address of PC1 and the destination MAC address of PC2. PC1 transmits the packet to the switch, looks at the MAC address table on the switch and checks if there is a destination MAC address. And here it learns the MAC address of the PC2 from the switch 2 because gigabit 0/1 is connected, and it learns the MAC address of the PC2 from the switch 2 and sends the packet to switch 2. Sends, switch 2 receives packets, and looks at the MAC table, and in the MAC table fast Ethernet 0/2 it has the MAC address of PC2 and forwards it to that user. In simple terms, the Ethernet frame is encapsulated in this way and this packet is extracted and transmitted in front of it. Ethernet addressing is also like this. Briefly, I will explain the binary number system, hexadecimal and decimal numbers again in our following lessons. Now let's look at half and full duplex and then finish our lesson. To understand the logic of half duplex, we need to look at an old device called the hub. When IEEE introduced 10BASE-T in the 1990s, the switches didn't exist yet, and then the old devices called hubs were used. We can consider these devices as layer 1 devices. When these devices received an electrical signal from one port, they would transmit this electrical signal to all ports. There would be collisions called collisions because they tried to transmit the packets to each port at the same time, and devices called switches were developed to prevent this, and this problem was prevented. Here's an example of an old hub, where you can see that user Bob and user Archie send packets to Larry, but because the hub device repeats all the signals that come here, two packets don't go away at the same time and there is a collision. Let's say this device is a switch and not a hub. Then when Bob and Archie send packets to Larry at the same time, the switch can queue them up and forward them. So it doesn't cause any collisions or packet loss here. In the figure here, half and full duplex shows Ethernet working together. Switch 1 and switch 2 work full duplex, but since a hub is connected to the fast Ethernet 0/2 port of the switch 2, this port works as half duplex. Because the hub device here works half duplex works on this port of the switch, but the other ports continue to work as full duplex. Users on the hub continue to work as half duplex, but our switches work as full duplex, while hubs work half duplex, that is, one way. That's why we no longer use hub devices in our networks, because they cause a vicious circle, congestion and collision of packets in our network, so now hub devices have completely disappeared and switches are used today. That's all we're going to tell you in this lesson, so goodbye to see you in our next lesson. Hello everyone, in this lesson I will tell you the basics of the wide area network. Wide area network, we call the wide area network that ISPs, that is, service providers, use in their own networks, WAN, and the networks we use locally are called local area network, or LAN for short. ISPs use various services in their wide area networks. One of these services is leaseline lines. We will talk in detail about the WAN architecture in Chapter 13 about other services, Metro Ethernet, DSL, MPLS, VPN over the Internet in Chapter 13 I will talk about in the WAN architecture section. Now let's talk about lease line. As you can see in the figure here, it shows the example of lease line in a simple corporate network. Why we need a wide area network? Let's talk about it first. We use wide area networks to connect our remote offices and our head office, because we may not be able to connect our networks by pulling cables between our remote office and our head office. We build our own local network in nearby places, for example, within the campus, but we cannot pull cables from the streets or alleys to our remote office. And we can connect our offices by using the existing infrastructure of the service providers and getting a service from them. We connect our remote offices. ISPs use various technologies to provide us with these services. Now let's look at leaseline from these technologies. Lease lines use the HDLC protocol by default, stands for High-Level Data Link Control Protocol, which is similar to the Ethernet technology we use in the local area network environment. The figure here illustrates the use case of lease line in a simple enterprise network. We have the remote office here, we have the head office here. It shows that we connect our remote offices between our head office and our remote office using the ISP's infrastructure, that is, using the wide area network. Let's look at the figure below, which shows in a little more detail here. We rent one lease line from telecom, that is, you rent a special line. The telecom company gives you this special line over 2 pairs of telephone cables, so you can get this service over a total of 4 wire telephone cables. After you get this service, you put one modem in the remote office and one in the central office, and in these modems we usually use Telabs brand modems. I say we used to use them because lease lines are not used much today. Technologies such as Metro Ethernet, MPLS, VPN over the internet are used now, but there are still places where lease line is used because the customer has bought these lines before and may still be using them, or you can have an office in a region where you cannot get Metro Ethernet or internet, then you can still use lease line over phone lines. In short, the lease line connection works in this way. You can provide this service using phone lines. You provide the connection by putting a modem between 2 locations. These modems usually have serial interfaces, and we use lease line lines by connecting these interfaces to your router. Lease line lines are a technology that serves us at layer 1, meaning it does the job of transporting bits. Let's look at the details of HDLC data link used in LeaseLine on this page. We said that the LeaseLine service is a service that serves in layer 1. It takes, moves and transmits bits and works in this way. For this, it uses the HDLC protocol, which is similar to the protocol we use in Ethernet. If you remember in Ethernet, we used frames, and here we also have HDLC header and HDLC trailers, or HDLC encapsulates the IP packet. If we look at our examples here, you can see how a router transmits data over the WAN. First, let's look at the way we look at the above. In this example, the packet is sent from PC1 to PC2. PC1 first sends the packet to router 1 so that the packet can go. Router 1 receives the packet and transmits it to router 2 over the WAN. Router 2 forwards the incoming packet to PC2. Let's look at a little more detail in the figure below. The yellow part you see here is our local network. Here we use Ethernet technology. Our user here takes the packet into the Ethernet frame and transmits it to router 1. Router 1 looks at the incoming package. If the package has come to it and there is no change in the FCS area in the trailer part, it takes the IP packet by removing the trailer and header part of the package. After receiving this packet, it sends the IP packet to router 2 by adding the HDLC header and the HDLC trailiness at the end, as it will transmit it over the lease line. After receiving this packet on router 2, it will send it to PC2 via Ethernet, so it transmits this packet back to PC2 by enclosing it in the Ethernet frame. Let's look at the use of Ethernet over WAN on this page. When Ethernet first came out, it was only suitable for local area networks, because we could only use up to 1 to 2 kilometers due to cable lengths and restrictions on devices, but now both cable technologies have developed and hardware technologies have developed, so ISPs can now use Ethernet over WAN technology. When we look at the example below, you can see the network of a service provider. Service providers can serve with Ethernet technology over WAN by pulling fiber optic cables to POP points and putting switches in them and pulling fiber optic cables to their customers through these switches. This is the topic in this lesson in a nutshell. We will revisit the details of the WAN topic in chapter 13. That's all we have to say in this lesson for now, so goodbye to see you in our next lesson. Hello everyone, in this lesson we will cover the basics of IP routing. We will revisit the details of IP routing in chapter 6. Now let's first look at an IP. What is an IP? IP stands for Internet Protocol. The Internet Protocol is actually the network layer itself. Other protocols in this layer exist only to support the Internet Protocol. IP determines where to send a packet by selecting the best route in the routing table. Now let's look at the routing forwarding logic in network layer. Routing forwarding logic is realized through TCP/IP installed software on our computers. When hosts send a packet, they try to send it using the TCP/IP networking model. In the TCP networking model, there are IP addresses, host's IP address, subnet mask, and default router IP addresses. When the host sends the packet to another network, it first forwards it to its default router, receives this packet in the router, checks the routing table and forwards the packet. In short, this is the working logic. Now let's understand it in more detail by looking at our example here. Let's look at how PC1 sends packages to PC2 here. The PC here is not directly connected to the one router, which means that the line symbol we see between them has a switch once in a while. Anyway, when we are going to connect a PC to a router, we need to connect it with crossover cables. I explained them in the cabling section. We use a crossover cable when connecting a switch to a switch. We use a crossover cable when connecting a router to a router. We need to use a crossover cable when connecting a host to a router, but we don't connect the PC directly here anyway. PC1 sends the packet to its default router. the default router IP is already in the IP information part of the PC. The PC sends the packet to its default router to forward it to another network. The default router receives the packet and sends the packet to router 2 by looking at the routing table. Router 2 sends it to router 3, router 3 forwards it to the PC. Now let's examine in more detail in the figure here. Let's first look at step A. In step A, PC1 takes the packet into its Ethernet frame and transmits it to router 1. Router 1 first checks this incoming Ethernet frame. If you remember, there was a trailer at the end of the Ethernet frame, and this trailer had FCS in it. First, the router checks the FCS. If there is a problem with the FCS, it drops without taking the packet anyway. After checking the FCS, it checks to see if the destination MAC address in this Ethernet header is itself. If the packet has arrived at it, it accepts the packet and discards the Ethernet header and trailer and removes the packet and looks at the destination address in the IP packet. The destination address is 4.10, i.e. 4.0 subnet. When the router checks the route table, the 4.0 subnet shows the IP 150.150.2.7 in serial 0/0 as next hop, then it will send the packet from the serial interface to the router 2. What does it need to do for this? Since this interface is a serial interface connection and we think that the HDLC protocol is used in this interface, but you can also use the point-to-point protocol, but the default protocol is HDLC. It sends the HDLC header at the beginning to the router 2 by adding the HDLC trays at the end. Router 2 likewise receives the packet, checks the route table, and sends it to router 3 via fast Ethernet 0/0 as the output interface. Router 3 checks the 150.150.4.0 subnet by looking at the route table, and since this subnet has a direct connection on itself, it sends it directly from the gigabit 00 interface to the PC2. The packet leaves PC1 and travels through the network by checking the route tables on the routers until it reaches PC2. Now let's look at the IP header in this IP packet, then let's finish our lesson. If you remember, data, it comes from the application layer to the fourth transport layer. The transport layer adds TCP or UDP header information and sends it to the third layer, the network layer, where the IP packet is added, and in the second layer the Ethernet header is added. This is the information in the IP header added to the beginning of the packet at the network layer. As part of the CCNA tutorial we will focus on the source IP and destination IP address parts. This is our data field from the third layer. This data is transmitted to the default router by adding the Ethernet header to the beginning and the trailer at the end, and the router checks the routing tables and chooses the best way from the routers to the routers, and finally the data reaches the user. That's all we'll tell you in this lesson for now. We'll revisit the details of this topic in Chapter 6, so goodbye to see you in our next lesson. Hello everyone, in this lesson I will tell you about the other services in network layer. In our previous lesson, we discussed IP routing in layer 3. In fact, the main master of the network layer is IP, but there are other services that work in this layer, and these services are the services and protocols that help the Internet Protocol. These are also DNS, ARP and ICMP protocols. Now we will cover these issues in this lesson. Let's look at DNS first. DNS stands for Domain Name System. Domain Name System, we use computer names, in particular to resolve the names of web servers or other servers. When we normally go to a server, it is difficult for us to keep in mind the IP address of the server. For example, is it easier to keep the IP 150.145.15.15 in mind to go to Cisco.com, or is it easier to keep Cisco.com in mind? Normally, we cannot access the server by typing a name, because we access the server with the IP address of the server, but we need to know this IP address before, and the domain name system has been developed because we cannot keep these IP addresses in mind. We first ask the domain name server for the IP address of the server we want to go to. When the domain name server tells us the IP address of that server, and we can access that server. Let's look at the figure here to understand how domain name server works. In this example, PC11 wants to go to server 1, where server 1 is called server 1. PC11 goes to the DNS server first and wants to know the IP address of server 1. The DNS server also immediately looks at their table, sees that the IP address of server 1 is 10.1.2.3 and forwards the IP of server 1 to the user to PC11. After receiving the IP information of PC11, forwards the packet to the server. This is how the domain name system works in a nutshell. For example, when you go to Cisco.com, you first go to the DNS server and you want to know the IP address of the server where Cisco's web page is. The domain name there gives you this IP information in the service, and you go to that server with this IP information. Normally, when you type Cisco.com, you cannot go to the server, because you need to go to the IP address of that server, and you learn the IP address from the domain name service. On this page, let me tell you about the Address Resolution Protocol ARP. What does the Address Resolution Protocol do? ARP allows us to learn a user's hardware MAC address from a known IP address. When we look at our example here, router 3 will transmit a packet to PC 2 over Ethernet. As you know, in layer 2, data packets are transmitted with MAC addresses in Ethernet frames. Therefore, in order for this router to send the packet, it must first learn the MAC address of the target, so this router needs to learn the MAC address of the PC here. Router, to find out the MAC address of the PC2, it broadcasts an ARP message on the network, and the PC2 sees this message and returns this request and forwards the MAC address to router 3. Router 3 also encapsulates the packet in an Ethernet frame and sends it to PC2. In other words, it is a protocol that allows to learn the hardware address of the user from a known IP address. Let's take a look at ICMP on this page. ICMP stands for Internet Control Message Protocol. ICMP runs at the network layer, just like IP, but it is actually a service that helps IP at the network layer. This protocol is a management protocol. We use it to detect problems that occur on user machines in our network. ICMP has some types of messages, so let's take a look at them. First, let's look at the unreachable message. For example, the host A user sends a ping to host B, but since the Ethernet 0 here is disconnected, the lab B router returns the message destination unreachable to the ping. Let's say you have pinged here and the router here has full memory, you will receive a message called buffer full. If you are receiving a hops message, you can tell that the IP packet has exceeded a certain number of routers, known as hops, that it must pass through. Packet Internet Groper i.e. ping, are the messages we use to check the physical and logical connectivity of our machines, that is, to check whether our machine is working or not. Traceroute is a type of message that we use to see or find the path that a packet takes through a network community. ICMP is also a very nice protocol. ICMP is a very nice protocol. It is a common protocol that we use a lot to troubleshoot problems in the network, especially we use traceroute and ping commands very often in our routers and switches and machines. The traceroute command is referred to as traceroute in the router, but it is used as trace or tracert on Windows computers. So many friends in this lesson, see you in our next lesson.